So today I'm going to talk to you about the art of authentication for web applications. Let's say it's your first time adding authorization and authentication to an application. And I really liked this tweet from Nick Craver from a few years ago. It says, step 1, are you ready to work on the auth code? Step 2, new dev says, hell yeah, bring it on. And then the lived experience often ends up looking something a little bit more like this. So here's the thing. The first time that you need to deal with something like authentication and authorization, you probably do what every great developer worth their salt does, is you Google how to do it. And then you're inevitably overwhelmed by just the sheer breadth and the volume of different types of auth, different auth providers, different authorization flows for different types of applications. And you're supposed to just kind of automatically know and understand which things you have to pick out from this ecosystem in order to implement and get to a fully realized auth solution. Now, this two-step process is actually feasible as pretty much a two-step process if you use something like an identity solution. But maybe you've never done that before, or maybe you're in this talk because you've implemented auth before, but what was actually happening and why it was happening was kind of a black box to you. You did a bunch of things and they worked out, you got a solution, but you weren't necessarily confident in your knowledge of why things worked the way that they did, or about what was happening under the hood. So today I want to show you how to draw the owl. I'm going to go into the foundational concepts behind authorization and authentication. And like I said, you don't need to be an expert in all of this to get to the end result. It can be a two-step process. But what I really want to do for you today is pull back those curtains. And in order to do that, we kind of have to start with an introduction to commonly used open standards. I'm going to go through this in what's hopefully an approachable way and really provide you with a foundational knowledge on standards-based authentication and authorization. I'm going to begin by covering some terminology. First, let's talk about identity. Identity means a lot to a lot of different people, but it's also kind of a blanket term for basically everything I'm going to talk about today. And more specifically, I want to define digital identity. Now, digital identity refers to a set of attributes that define an individual user in the context of a function that's delivered by a particular application. So that's a bunch of words, but as a practical example, let's say that you are an online shoe retailer. The digital identity of your users in this context is probably going to be something like their credit card number, their shipping address, and maybe their purchase history, because these are the things that are relevant to your application. Now, when we say authentication, what do we mean? Well, in a broad sense, authentication is the process of verifying that the user is who they say that they are. And this takes us to authorization. Now, these two terms are often conflated. Sometimes they are used inappropriately as one being actually the other. They're not the same thing. Authorization is about granting or denying rights to access resources. So here's a metaphor. If you're going to travel by flight, you're going to take a plane somewhere. When you get to the airport, you authenticate at security by providing your ID or your passport to the TSA agents. You prove that you are who you say that you are. Then you go to the gate, and when you go to get on the plane, you're going to present your boarding pass to the gate agent, and this is authorization. This grants you access to the airplane. So if we return to the ecosystem of web and web application, this concept of authorization brings us to the OAuth specification. Unfortunately for us, OAuth standards are very clearly defined. Also, unfortunately for us, they're also very dense, and they can be pretty difficult to grok if you just pull them up and start reading them. So one of the things I want to do for you is demystify OAuth. And in order to do that, we kind of have to talk a little bit about why OAuth was created in the first place. What problems did it solve for us? So here comes a little bit of a history lesson. Before OAuth 1.0 was established in December of 2007, if we wanted to access third-party resources from one application in another application, then it looked a little bit like this. And I'm going to use some example apps that don't really exist. I kind of struggle with naming them because there are a lot of apps out there, and it turns out most of the names of apps are actually taken. But let's say you use a web app called Hire Me. The 1, 2, 3 is because there's actually an app called Hire Me. But you use this app to search for and apply for jobs. Maybe you use it to connect with recruiters and hiring managers, and maybe you can schedule interviews. Now let's say you also use an app called MyCal app to manage your personal calendar. And let's say that Hire Me wants to add an event to your MyCal. Maybe you've set up an interview. The application Hire Me now wants to be able to put that interview on your calendar in MyCal. So historically, what would happen first is that Hire Me would ask you, the user, for your MyCal credentials, your MyCal username and password. You would give your MyCal username and password to Hire Me, and then Hire Me would take your credentials and it would use them to access the MyCal API, basically as you. At that point, Hire Me could access the API to create calendar events using the access that you gave it by sharing your MyCal credentials. This is bad, right? This approach relied on sharing a user's personal login information from one application with a completely different application. I think we can all agree that's really not a good idea. For one thing, if Hire Me doesn't do their due diligence, they really have a lot less skin in the game than MyCal. So, for example, if Hire Me was to suffer something like a data breach and all of the MyCal credentials ended up getting stolen, this is catastrophic for MyCal. But Hire Me might just get a little bit of bad press, but it's not their credentials that got stolen, so it's not that big a deal to them. Hire Me also has way too much access to the MyCal API. By using your credentials, Hire Me can do everything in MyCal that you can do as a user. So it could delete events, it could change settings, it could access your phone number. If you have a subscription to MyCal, it could even see your credit card number and things like that. So we can all agree that this wasn't any good. And this is where OAuth comes in. So we needed a solution for this situation. In this talk, I'm specifically going to talk about OAuth 2.0. And using OAuth, MyCal can now do something like delegate authorization to Hire Me. It can give limited access to Hire Me to the MyCal API without incurring the risks of exposing credentials. And it does this by using something that we call an authorization server. Now, an authorization server is kind of a fancy word to refer to a set of endpoints that interact with the user and issue tokens. And it does this in order to perform what we call delegated authorization. Delegated authorization allows a party that holds some authorization to delegate a subset of that authorization to another party without requiring either party to disclose any user credentials to the other. But how does this actually work then? Well, let's go back to our example with Hire Me and MyCal, only now we have OAuth 2. That means that MyCal now has this thing called an authorization server. And for the purpose of this example, we're going to assume that Hire Me has already registered as a known client with MyCal, and that just means that MyCal and MyCal's authorization server are aware that Hire Me is an application that might be asking for access to the MyCal API. And let's say that the user's already logged in with Hire Me. And now Hire Me wants to set a calendar event on your MyCal calendar. Maybe it's that interview event. The first thing that happens is the browser is going to perform a GET to send an authorization request to MyCal's authorization server. the MyCal authorization server will prompt the user to log in with MyCal, and if you're not already logged in. So the user is going to authenticate with MyCal. And then the MyCal authorization server can prompt the user in the browser for their consent to allow HireMe to access the MyCal API on their behalf within the scope of adding an event, and not more than that. The user has to agree to this, and if they do, then MyCal's authorization server can send an authorization code to HireMe in the browser. And HireMe is going to take that code, and it's going to take its application credentials that verify its identity to MyCal, and it's going to send these things back server-side. MyCal then checks to make sure everything is okay with this, and if it is, it issues an access token. And HireMe can then use that access token to access the MyCal API. But it can only do this within the scope of the permissions that have been accepted by the user. So that means that HireMe can now set calendar events for the user by using the MyCal API. And nothing insidious is happening now, right? MyCal is asking the user to log in with MyCal. HireMe is not asking for your MyCal credentials. And HireMe can only create events, not do other things like read all of your events or change your settings. So we have the problems with sharing credentials and too much access being given to third parties. They're basically solved. They're no longer a problem. But then, we liked this idea of using an authorization server so much that apps wanted to do more than just call APIs. They wanted to be able to sign users in with accounts that actually lived in these other systems. So for example, maybe HireMe wants a MyCal user to be able to log into HireMe using their MyCal account, despite not having a HireMe account. And we can see this as a need because now we do this all the time, right? But remember, OAuth 2 was a specification for delegated access. It's not an authentication protocol. So if HireMe does something like use the access token that it was given to call the MyCal API and assume that by calling that API, it can assume that the user can be considered authenticated with HireMe, then we start to run into problems. Access tokens are for API use. They are opaque to the client. So we don't know what is actually in this access token. So HireMe could have a token that was actually stolen from somewhere else. The token could be for a completely different user. It could have been obtained for another client that's not HireMe and then injected into HireMe. And we call this the confused deputy problem. HireMe doesn't know inherently where this token came from or who it was issued for. And authentication is about verifying that the user is who they say that they are. HireMe can't know this from using an access token to call an API. Access tokens are for authorization, access to resources, not verifying identity. However, this didn't stop companies from doing this anyway. So the need arose to formalize authentication on top of OAuth. And as you know, we did this. Modern apps do this all the time. We often log in with Google, with Twitter, Facebook, etc. So clearly this problem has been solved. And it was solved by the creation of a new specification, or new at the time, called OpenID Connect. Now remember, OAuth 2 is for delegated authorization, so OpenID Connect is for authentication. It's easy to get these concepts and specifications confused with each other, though, especially because their flows and details are built on the same foundation. So OpenID Connect, or OIDC, is an identity layer on top of OAuth 2 that tells us how to authenticate users using an authorization server. Now, in both specifications, the role of an authorization server is to issue tokens. So let's talk a little bit more about tokens specifically. And for authentication with OIDC, we use ID tokens, which makes sense because we're identifying the user with it. So our authorization server can issue ID tokens similarly to the way that it issues access tokens, which I discussed briefly in the first example with HireMe and MyCal. However, unlike access tokens, ID tokens are actually intended for the client. ID tokens are a fixed format, and they are fixed formats that clients can parse and validate in order to extract identity information from the token and therefore authenticate the user, verify the user is who they say that they are. Now, OAuth 2 describes how access tokens are issued and managed, and OpenID Connect extends OAuth 2 to show how to issue and manage ID tokens. Like I said, the OIDC spec declares a fixed format for ID tokens, and this format is JSON Web Token. So let's dig into JSON Web Tokens, what they contain, and why this format is useful for ID tokens. JSON Web Tokens, or JWTs, which is also often pronounced JOT, because I guess JWT is too hard to say, they look like this. They're 3 string segments concatenated with periods. The first segment is called the header segment. This is a JSON object, and this object contains an algorithm and a token type. Then we base64 URL encode this object to make it URL and file name safe. The second segment is called the payload segment, and these are data claims. This is an object that contains statements about the user and also about the authentication event itself. Again, this is also base64 URL encoded. And the final segment is the crypto segment, or the signature. Now, JSON Web Tokens are signed so that they can't be modified in transit. This is the RS-256 signature, which I'm going to cover. And if you recall, this was cited as the algorithm that was provided in the header segment JSON object. And RS-256 is a known entity. So knowing which algorithm to use enables us to validate the signature. And I'm going to give you a little peek into the contents of the black box here. I'm going to go through how the signature is created and show why and how it gives us the confidence to know that a token is trustworthy. So we take the first 2 segments of the JSON Web Token. This is the base64 URL encoded header and payload. And these 2 things together are the signing input. We know that the signature algorithm we're going to use is RS-256. This means that we can use the SHA-256 hash function in order to hash that signing input. Now, hashing is irreversible. If we take a hashing function and we put one input into it and get an output, if we put that same input in, we'll always get the same output. But no 2 different inputs will result in the same output, and there's also no way to get back to the input once you have the output. RS-256 is an asymmetric signing algorithm, and this means that we use 2 keys with it. So we're going to encrypt the hashed header and payload, the signing input, using a private key. But then unlike hashing, encryption is reversible. We can decrypt the result if we use another public key, and we can get back to the original input. And only the token issuer, in our case this is the authorization server, has access to the private key, and the private key is used to sign the tokens. So this is the creation of this signature. Then when the client receives the JSON Web Token, it's going to validate the signature using its public key. So how does this signature ensure that the token wasn't modified in transit? Well, in order to validate the signature, the client is going to take the header and the payload from the token that it received. And since it knows the signing algorithm from the header, it can use the SHA-256 hash function to hash these 2 segments. It's basically performing that same step that the authorization server performed. And this gives us that same hash that the authorization server then encrypted in order to create the signature in the first place. Now, because encryption is reversible, clients can decrypt the signature using the public key, and this gives us the signature hash again. We then have the ability to compare the hash that we just computed on the client side with the hash that we decrypted from the signature from the token's crypto segment. And if these two match, then the token signature can be considered validated. And in this way, we can be sure that nothing in the header or payload changed between the time that the token was issued by the authorization server and when it was received by the client. But it's a lot, right? The decoding, the hashing, decrypting, comparing them, and typically we wouldn't do this validation manually, step by step in our applications. A lot can go wrong, it's also complex. So instead, we would want to use a JSON Web Token library or an Identity Services Client SDK to handle all of this for us. So now we have validated the ID token data, which means that we have access to it and we can actually use it in our applications. Now, the payload segment contains most of the useful data, and this is a JSON object with claims in it. These are statements about the end user and statements about the authentication event itself. So if we talk a little bit about the authentication claims, they might look something like this. You have something like an issuer. This is the name of your authorization server. It's where the token came from. You have an audience. This is the unique ID of the application that the token was issued for. We have some timestamps. These tell us when the token was issued and when it expires. And then we have this thing called a nonce. And a nonce is a cryptographically random string that binds the client to the ID token that the client receives. The way it does this is that the client generates the nonce and sends it to the authorization server with its authorization request. And the authorization server then takes this nonce that it received with the request, and it puts it inside the token that it issues and sends back to the client. Then when the client decodes the token, it can check that the nonce in the token was the same nonce that it sent to the authorization server in the first place. And this protects us against something called token injection, which is tokens that are coming from somewhere other than the authorization server. If we can't bind the request with the token that we get back, we should throw it out immediately and definitely not trust it. So in addition to validating the signature itself, clients need to make sure that they're verifying the authentication claims that are contained within the token, like the issuer, the audience, the timestamps, and the nonce. And once we've done all of that, we can basically trust that the token contents are reliable and can be used. So that brings us to kind of the meat and potatoes of the ID token. This is identifying information about the user. And ID tokens contain statements about the end user. Some of the standard claims in the specification that we can ask the authorization server to include about the user are things like the subject. This is a unique user identifier. And then we have other profile information. This can be things like address, nickname, avatar photo, email, website, so on and so forth. So now that the user is authenticated and we're ready to call a resource API, I'm going to cover access tokens in a little bit more depth. Now remember, access tokens grant access to resources. In our example, we used the access token to grant access to the MyCal API. And unlike ID tokens, which are JSON Web Tokens as per the OIDC specification, access tokens in OAuth 2 actually have no specific defined format. They don't have to be and aren't necessarily JSON Web Tokens. However, many authorization servers do use JSON Web Tokens. This includes like Auth0, Amazon Cognito, Ping Identity, Microsoft Identity Server, Okta, and others. Most of them do, because the format enables validation, which I just demonstrated. Now, like I said, access tokens are for the resource API. Unlike ID tokens, they're opaque to the client. So the content in an access token can actually change at any time. Because they grant access to a third party, they should be treated very carefully. They should have a short expiration time, And that resource access that they grant may actually change throughout the user session as well. So the client should never have code in it that relies on the content of an access token. So what does API access look like with an access token? Well, we have the client logged into the client, or the user logged into the client application. We have our authorization server. And then we request an access token to get resources from an API. When we call the API to request data, we attach the access token to the request. That request gets sent to the API with the access token. And the API then can take validation steps in order to validate the token using middleware before it returns any data. If everything checks out, the data can then be sent to the application. But when we're dealing with delegated authorization, how does the API know what level of access it should give the application that asked it for resources in the first place? Well, we do this with something called scopes. So remember this part of the sequence. We only want HireMe to create calendar events with the MyCal API, but not do more than that. So in order to solve for this, scopes limit what an application can do on the behalf of the user. Scopes can't grant privileges that a user doesn't already have. So if the user, for example, doesn't have a privilege to set up, let's say, enterprise MyCal accounts, then any scopes that are granted to HireMe as an application will never allow the user to set up enterprise accounts either. We delegate access control to the API or the resource. And then the API is actually the responsible party for combining the incoming scopes with the actual user privileges. Then the API is the one that's going to make appropriate access control decisions. So to show you what this looks like, let's say we have a user using an app, maybe it's HireMe, and we want to access third-party resources on the MyCal API. Let's say we've already acquired an access token from the authorization server, and the token received from the authorization server already contains user identifier and an audience saying that the token was issued for the HireMe client, and then it has a scope for permission to write calendar events. We send this request to the API, and we have this write events permission listed in our scopes. But the MyCal API can access everyone's calendars. It can access hundreds of thousands, maybe even millions of different users. So in addition to looking at the token scope, the resource API is responsible for using something like the subject identifier in order to only allow the user to exercise their own capabilities and not interfere with other users' calendars. So in the context of delegated authorization, scopes express what an application can do on the user's behalf. They are a subset of the user's capabilities. Remember when we prompted the user for their consent for MyCal to allow HireMe to do certain things? More realistically, that consent dialog might look something like this. HireMe could ask for a variety of different scopes, but you shouldn't overload scopes with user-specific permissions because scopes are intended for app-level permissions. So what have we learned so far? We've taken this concept of authentication and authorization and going from a vague idea to a more complete solution, we filled in a lot of the concepts and background, including OAuth 2, OpenID Connect, authorization servers, ID tokens and the JSON Web Token format and how to validate them, access tokens, and scopes and delegated authorization. So next I'm going to talk about the implementation of authentication in web applications. But first, this is kind of a dense talk, so I'm going to take a little break. My name is Maida. I am a Google developer expert in security, privacy, payments, and identity. I'm also a GD in web technologies. I'm an Auth0 ambassador, and I was the former head of developer relations at Auth0. And I'm currently the VP of developer relations at Ionic. As a hobby and side gig, I make detailed miniature food, jewelry, and dioramas. And I also sculpt and resin cast artisan keycaps for mechanical keyboards. Finally, I draw and design stickers, which I then take with me to conferences that I speak at and I give away to people. So come talk to me if you want some free stickers after the talk. Okay, back to the main topic. I want to talk a little bit now about authentication for web applications and how we implement login with different application architectures. And first, I'm going to talk about authentication in what we call traditional web apps. These are server-side web applications that are written in languages like PHP, .NET, Java, so on and so forth. This is classically cookie-based authentication. In these types of architectures, we have the browser. And then on our server, we have our backend web application that probably has an API and access to a database. And then in the context of OAuth and OIDC, we have an authorization server. Now, using the browser, the user is going to authenticate by providing their credentials, and an authorization request is sent to the authorization server's authorization endpoint. Remember, authorization servers are a set of different endpoints. In response, the authorization server is going to issue a code, and then it redirects the user back to the app with the code. The app then takes this code, its client ID, and its client secret, and sends them to the authorization server's token endpoint. These are all verified by the authorization server, and if everything looks good and checks out with them, then the authorization server will issue tokens which are stored securely in the server-side application on the back end. The server then is going to set a cookie in the browser, and this cookie represents the user's session. The user is now considered authenticated and has access to data. Then on any subsequent requests for pages, whenever there's traffic to the domain, the cookie is attached by the browser and it's sent to the server. The application then gets sensitive data from the API with the access token, and requested page HTML as well as any sensitive data can be sent back to the user in the browser. Now, if the cookie is expired or there is no cookie and a request is made for any of this protected data, then the server is going to return a 302 redirect status. The browser is going to do a full page redirect so that the user can re-authenticate. And then once they've done that successfully, secure data can be sent again. So there's another type of web app that's become very predominant on the internet these days, and that's single-page applications that are built with JavaScript. These applications are often secured using what we sort of generally refer to as token-based authentication. It's a little bit of a misnomer because everything is token-based, but I'm going to cover an overview of the general architecture, and then I'm going to get into details in a little bit. But in this architecture, we have the browser, and then when the user navigates to the application, the app is actually compiled, downloaded, and runs in the browser. Then we get resources from an API, and we have an authorization server. Now, when the user wants to log in, we're going to make an authorization request to the authorization server. The authorization server is going to verify the credentials, and then it's going to issue tokens, either an ID token alone or both an ID token and access token. These tokens are then delivered to the single-page application that's running in the browser. And authorization servers can also set a cookie in the browser for the domain of the authorization server. And this represents the user's session with the authorization server. In the client, the ID token is then parsed and validated, and the user is considered authenticated and everything goes well with this. Tokens should then be stored in application memory. It's recommended that we don't store tokens in local storage because they're vulnerable there to cross-site scripting, and they're also accessible to any app on the domain. Then when the app makes HTTP requests to the API, the access token is included in the authorization header. The API verifies the access token using middleware, and data is returned usually in the form of JSON, and the application can consume and display it. But in a single page app, if the page is refreshed, then the whole application reloads. And if we don't have user info or tokens anymore stored in our app memory, then we can actually use this authorization server cookie to check if the user's authorization server session is still valid. If it is, the app can use an iframe and the authorization server cookie, and without prompting the user for their credentials, it can silently request new tokens without user interaction. This is called silent authentication. However, a more recent challenge with this is that browsers have started implementing privacy measures like intelligent tracking prevention in Safari, and these measures block third-party cookies. So recall, this cookie is for the authorization server's domain, not the application's domain, so it's a third-party cookie. And ITP blocks silent authentication if it's turned on, and we're back to asking the user to re-authenticate all the time, if they even just hit refresh. If they leave the app and come back in an hour, they'll have to re-authenticate. And this results in a less than ideal user experience. Users don't want to log in every time they have to come to an app. So there's an additional token type that I'll discuss, and that is refresh tokens. Refresh tokens are credentials that are used to obtain new tokens from the authorization server without making the user re-authenticate. The client presents the refresh token to the authorization server. The authorization server then authenticates the client and validates the refresh token. And then if the validation is successful, the authorization server can issue new access and ID tokens. And again, this is used without user intervention. The user doesn't have to enter their credentials again to make this happen. So historically, the problem with using refresh tokens in single-page apps is that they're long-lived. They also can't be stored securely in the browser. And in the past, the security risk of refresh token use in the browser wasn't acceptable. So this is why we created silent authentication. This is a way to be able to keep users logged in without the use of refresh tokens. However, authorization servers now support something called refresh token rotation. And this is done to enable public single-page apps to use refresh tokens that are invalidated after a single use. So a new refresh token can be issued every time a new access token is issued. And authorization servers also have come up with automatic reuse detection. And this reduces the threat surface. And it also does this neat thing where it enables refresh tokens to be stored in local storage, unlike access and ID tokens, when they're used in conjunction with modern best practices for securing single-page apps. And I will cover that shortly. But first, why can't we just use cookies for single-page apps? Similarly to the way that we would do so in traditional server-side apps. Cookies only work on the domain of the application. If everything is on the same domain, then cookies will work. But many single-page apps call APIs that either live on other domains, or if they don't now, they might need to do so in the future. But if you do call an API that lives on another domain, your domain's session cookie is not going to work for the domain of the API. But maybe this isn't actually a problem for you. If your single-page app and your backend live on the same domain, And this is pretty common, right? For example, maybe you have an Angular app that runs on .NET backend, or a React app with a Node backend and an API, and you're only exposing your API for the exclusive use of your presentation layer, which is the single-page application. And if this is your architecture, then cookies can actually work. You can use cookies. It will look like this. We have a backend, and the backend is capable of executing code, and it also provides our API endpoints. The backend probably also serves the single-page app, which then runs in the browser. And then we have our authorization server. We can use backend routes to log in, and the backend application can be the entity that interacts with the authorization server to authenticate users and also store tokens. Then the data that's moving between the backend and the single-page app can be secured with an HTTP-only session cookie. You don't have to be exchanging tokens with the browser. But maybe you need to scale. Maybe you have a JavaScript app that doesn't have a backend, or maybe you have a JS app that calls APIs that live on other domains. And if this is the case, then you will need to use tokens. So I want to talk about the guidance for token use with single-page applications. And in order to discuss this, we have to do another little bit of a history lesson. Because in 2012, when OAuth 2 was adopted, this was 20 years ago. It was not 20 years ago. It was 10 years ago. But that's like decades and decades in tech time, right? So in 2012, which was 10 years ago, because I can do math, when single-page apps weren't mainstream yet. So for example, AngularJS didn't become popular until about 2014. And AngularJS is kind of one of the older frameworks that has morphed but is kind of still around, right? So historically, when we use tokens for single-page applications, the tokens were delivered to the application in a browser redirect. We would make a request to the authorization server, and the authorization endpoint, which is the same endpoint that receives the authorization request, would then return the tokens to the browser in a URL hash fragment that is appended to your app's redirect URL without any additional steps. There's no code exchange or anything like that. And this is called implicit flow. The naming here makes sense because we don't confirm the request by exchanging any additional data with the authorization server. We instead implicitly accept the tokens without exchanging a code. There's security risks for putting access tokens somewhere like a URL. Access tokens grant API access to a third-party resource. Remember all of the problems I talked about with confused deputy. So access tokens in a URL are vulnerable in a number of ways. They're vulnerable in the redirect URI itself because we could redirect the token to someplace that it's not supposed to go, for example. They're also accessible in the browser history. And they're accessible in the refer header if a malicious page is requested right after an authentication event, for example. Finally, the application doesn't inherently know if this token was injected maliciously from somewhere else. So we're kind of back to facing all of the same problems with confused deputy. Now, authorization servers and app developers work pretty hard to mitigate these risks. And I talked about the importance of validating ID token signatures and then verifying the authentication claims. But we can only do this properly with ID tokens. Access tokens are opaque to the client. That means they can't be validated on the client side until an API request is made. And then the API validates them, and that's probably a little bit too late to just assume that they're safe until you send them to an API. Now, if you've been around the single-page app and the auth scene for a few years, you've likely used this flow, the implicit grant. And it's still okay to use implicit flow with form post. So this is a variation of implicit that returns data in an HTTP 302 instead of in the URL. But it's only okay if you're only asking for ID tokens because they can be validated in the client. If you need access tokens, you need to use a different approach. So as we know, modern JavaScript has really eaten the world of web applications over the last few years. And in early 2019, the IETF and OpenID Foundation, which are the groups responsible for OAuth 2 and OIDC, they started to update best practices for these specifications, specifically targeting JavaScript applications. And this is actually the same approach that we use in mobile applications, because mobile apps are also public clients. They're not capable of storing client secrets safely because they live on the user's device, not in a centralized secure location. So similarly, single-page apps are loaded into each user's browser. And this mobile and now single-page application flow is called authorization code with proof key for code exchange, or PKCE. And in this flow, we exchange a code for tokens. We do this similarly to the way we do it for traditional web apps, but because this is a public client, we need to take some additional precautions. And I want to show you kind of how this works and why it works. So we have our JS app. It's running in the user's browser. And we have our authorization server. And on the client side, we're going to create a random string. And this is called a code verifier. Then we have a hashing function called a code challenge method. And using this hashing function, we hash the code verifier string in order to compute another string, which is called the code challenge. When the user comes along, we take the authorization request and the code challenge method, and we send all of these things to the authorization server's authorization endpoint. The authorization server then generates a code, which is sent to the browser. And the browser receives this code in a URL query string. And it can do this because interception of the code by itself isn't dangerous. Alone, the code doesn't grant access to anything. You could take it and inject it into another application and nothing would happen. What it's for is enabling the next step. Once we have the code, then the code and the code verifier, which is that original cryptographically random string, are sent to the authorization server's token endpoint. The authorization server then confirms this code is the same as the one the authorization server sent in response to the app's authorization request, the one that was delivered in the query string. And it's already got the code verifier. Well, it just received the code verifier, which is the original random string that was generated by the client. And remember, we also sent over the code challenge on our initial pass, and we sent over the code challenge method. We did this with our initial authorization request. So the authorization server now is equipped to use the code challenge method to calculate the code challenge using the code verifier that it just received from the code exchange. It compares its calculated code challenge to the code challenge that the application sent earlier. And if these code challenges match, then tokens can be issued and they're delivered in a JSON object to the application. And this can be done because now we're interacting with the token endpoint. And this is an endpoint that is capable of sending responses via backchannel. This should feel a little familiar, right? Because it's kind of spiritually similar to how the client validates a JSON web token signature. And now all of those mitigations that we've been doing for security risks around putting the token in the URL are no longer needed. In addition, we can also use refresh tokens if we're using auth code with PKCE, as long as our authorization server supports refresh token rotation. But again, this looks like a lot of work, right? And a lot can potentially go wrong here. So similarly to how we would typically use a library to validate JSON web token signatures, we should really use SDKs or services to handle proof key for code exchange as well. We want to offload all of this stuff to security and identity experts so that you can spend your time building awesome applications that highlight the features that are unique to your application, rather than redoing all of this work that tons of applications have to do anyway. So what do these best practices mean for you? Well, new single-page applications should definitely be using PKCE at this stage, and older, well-maintained applications should migrate to PKCE if they haven't already. However, I do want to make it pretty clear that this didn't happen because all of a sudden all apps using implicit flow are in danger and there's some new security threat. Apps using implicit grant haven't suddenly become insecure as long as you're doing all of the risk mitigation that I talked about and that we've been doing for the last 10 years. So if your org still uses an old flow, this is your friendly nudge to explore updating if it's feasible. So I hope this talk has demystified the standards and the basics of authorization and authentication, as well as how to implement them on the web, why they kind of work the way that they do, and the reason that specifications have evolved over time to adapt to the things that applications want to do on the internet. So my Twitter's been in the corner this whole time, but if you want to connect and learn more about this stuff, I'm on Polywork as Kim Maida. I also have a blog at maida.kim, and I've written a few articles that cover these topics in depth if you want to review them, or if you would like to consume them in a written format instead of like in a talk. And I speak at a lot of conferences on a lot of different topics. One of the main things I talk about also is developer relations and career development for developer relations. So if you're interested in that, you can connect with me on that also. My speaking events and talk recordings are on my website, and they're also on GitHub. And I also build open source Slack apps and operations automation. This is something that I love to do for myself and for the companies that I work at. So if you're interested in that, check out the GitHub too. You can grab these slides here at the link, and they're in video format. That is to preserve the animated diagrams, but you can just visually consume them without listening to me talk about it. And please come talk to me if you want to chat about any of this, or if you just want stickers. I won't be offended if you come up and you're like, I just want stickers, I don't want to talk about anything else. So thank you so much for your time today, and I hope you have a great time at Stir Trek.